Hello everyone. Today I'll be discussing the approximate solution of initial value problems by using the Euler's method. Essentially, the Euler's method is the approximation of a curve using tangent lines, and the formula m at x0 and y0 is equal to rise over run, where rise is equal to y1 minus y0 and run is equal to x1 minus x0. The first step in the Euler's method is to make a small step size for x increments or run, denoted by the letter h. In this scenario, we have a graph for y equals x squared plus 1, where dy dx is equal to 2x, and y at 0 is equal to 1. We first approximate that the gradient of the tangent m at point x0 and y0 is equal to the gradient of the curve dy dx as a function of x0 and y0. Subsequently, we can manipulate m equals to dy dx to form the step size of y for every step size of x, and therefore find the next value of y. By inputting x0 into dy dx, we get our first point y1 equals to 1. We repeat the process by inputting x1 into dy dx to get a value of y2 equals 3. We repeat the process for y3 using the value of x2 to get y3 equals to 7. By connecting the dots, we find ourselves with a semi-accurate approximation of the curve. This result can be enhanced by using a smaller step size for x. This is because the variable dx in dy dx involves infinitesimally small increments of x. As such, the smaller our step size, the more accurate to the original curve. Here, by using a smaller step size of 0.5 rather than 1, we get an even more accurate representation of the curve. Now, in order to solve this initial value problem, we first input our initial value of x equals to 0, y equals to 1, and dy dx equals to x over y squared. Following that, we make use of a step size of 0.1 and copy in the formula for y1. We can then copy down all the rows until we see x equals to 1. We see that y at x equals to 1 is 1.339315, which is not far from 1.3572 derived by the general solution. Here, by using an even smaller step size of 0.005, we get a more accurate value for y at 1. An even smaller step size of 0.001 results in a substantially more accurate value for y at 1. This goes to show that the smaller the step size of x, the closer it is to dx, and therefore the more accurate it will be to the original curve. In summary, the Euler's method involves picking a small step size for x, equate the gradient of the curve dy dx at point x0 and y0 to the gradient of the tangent line m, and subsequently manipulate it to find the step size of y. This allows us to plot the curve with the new x and y values. Since our values for step size h will always be greater than the infinitesimally small increments of dx, our y values are delayed and lower than the solution at a particular x value. Thank you for watching.